All right, let's get right into it. Back in June of 1948, a super short letter gets published in a science journal. It's from two guys at Bell Labs, and honestly, it's a dense, really technical, two-page announcement that seems pretty modest. But hiding in those diagrams and data was the beginning of a revolution, something that would literally define the world we live in today. So we're going to dig into that original paper, slide by slide, and see how the transistor was born.
This is how they opened. No big fanfare, just a super straightforward claim. With this one sentence, J. Bardeen and W. H. Brattain basically challenged the king of electronics at the time, the huge, fragile, and power-guzzling vacuum tube. They weren't just suggesting a small improvement, they were proposing a totally solid-state replacement. And it's really hard to overstate just how radical of an idea that was.
So first up, a new electronic device. What is this thing they built? Let's peel back the layers and take a look at the actual physical setup of what they called a semiconductor triode.
Everything, and I mean everything, starts with this stuff, germanium. The paper is really specific, calling for an N-type semiconductor with a certain electrical resistance. Now, all N-type really means for us is that it's a material that just happens to have extra electrons hanging around, ready to carry a current. This specific little block of germanium is the stage where all the magic is about to happen.
And here it is, Figure 1 from the original paper. This is the blueprint for a revolution. I know, it might look a little like abstract art, but every single line and symbol here represents a completely groundbreaking idea. It shows three really important connections made to that one block of germanium. Let's break down what they are.
Okay, so this device has three main players, or electrodes. You've got the emitter, the collector, and the base. If you can wrap your head around the job that each one of these does, you've pretty much cracked a code of the whole device. So let's see how these parts are actually put together.
The physical details here are just wild. The emitter and the collector, they're just two tiny metal points like the tip of a pin pressed right onto the germanium. And check out that spacing. They are ridiculously close, just a few hundredths of a centimeter apart. That tiny gap is absolutely everything. The base is just a big electrical contact on the bottom of the germanium block. And that's it. That's the whole shebang.
So you're probably thinking, wait a minute. You have two little metal points super close together on a piece of germanium. How on earth does that amplify anything? Well, this is where the real magic and the true genius of this whole discovery really comes into play.
This is the fundamental question for any amplifier, right? How do you get more out than you put in? How can you turn a tiny electrical whisper into a great big shout? Bardeen and Brattain found a completely new way to do it.
Okay, the secret is all about how these 2 points are powered up. The emitter gets a tiny positive voltage, which makes it inject a small current into the germanium. You can think of it like just barely turning on a faucet. At the same time, the collector has a big negative voltage. This makes it act like a powerful drain, ready to suck in any current that gets nearby. The small input signal you want to amplify, you apply that to the emitter, basically just wiggling the handle on that faucet.
But what's actually flowing from that faucet? This is the secret ingredient they stumbled upon. They figured out that on the very surface of their N-type germanium, there was this unbelievably thin layer that had the opposite property, a P-type layer. And in this special layer, current isn't carried by negative electrons. Instead, it's carried by what you can picture as little bubbles, where electrons should be. These act just like positive charges, and they gave them a name, hole.
And this is where it all clicks. That small stream of holes coming from the emitter gets swept up instantly by the powerful negative voltage of the nearby collector. But as it flows, it's like a tiny rudder steering a giant ship. It modulates or controls the main current of electrons that's already flowing toward the powerful collector. So a small change in that little hole stream causes a much larger change in the big electron stream. And boom, that's amplification. A tiny input now controls a massive output.
Of course, a great theory is one thing, but the paper had to deliver the cold, hard proof that this little gadget actually worked the way they said it did. And here it is, their data. It might just look like a tangle of lines, but to an engineer in 1948, this graph was a masterpiece. It plots out all the relationships between the currents and voltages, showing exactly how the emitter and collector are interacting.
So let's just translate that graph into plain English. The lines prove that when you change the small emitter current, it definitely changes the larger collector current. And here's the kicker. The change in the output current can be way bigger than the change you put in. When you combine that current gain with the fact that the collector has a really high resistance or impedance, what you get is serious power gain. This was the proof.
So how much gain are we talking?
The paper puts it plainly. They got power gains of over 20 decibels. To put that in perspective for you, that's a power amplification factor of 100. The signal that came out was 100 times more powerful than the signal that went in. Their device didn't just work, it worked spectacularly well.
And this thing wasn't just a slow, clumsy amplifier either. They reported that it worked at frequencies all the way up to 10 megacycles. This proved it wasn't some lab curiosity, it was a serious threat to the vacuum tube, with the potential to be used in radios and other high-frequency stuff right out of the gate.
You know, an incredible technical achievement like this just doesn't happen in a vacuum. The paper itself actually ends by acknowledging the team effort that was behind this whole discovery.
Bardeen and Brattain made sure to give credit to their boss, William Shockley, for his leadership. And while these two were the ones who actually performed the specific experiment that finally worked, it was all part of a much broader research program. This one sentence is a great reminder that huge breakthroughs are rarely the work of a lone genius, but the result of a really dedicated team.
So the huge takeaway from this paper is this. For the very first time, amplification was achieved in a solid piece of material. It was tiny, it barely used any power, and it was tough as nails. This wasn't just an improvement, it was a total paradigm shift. And it leaves us with this one giant question. What would a world built on this tiny, solid-state amplifier look like? Well, the answer, of course, is the world we're all living in today.